Hello everyone and welcome to this week's OpenGL tutorial, and this week I'm going to be taking you through my implementation of low poly water. So low poly water is probably the largest topic that I've covered so far in these tutorials, and it involves a lot of different OpenGL concepts all working together to create this effect. Because of that, there are just so many different ways that you can do it, so many different effects that you could add, and so many different techniques that you could use. So this week I'm just going to be showing you my implementation of it. I can't promise you that it's the best implementation, but it's the best that I've managed to come up with so far. And of course, if any of you guys have ideas about how it could be improved, then please do let me know, because this is something that I use in my own projects, and I'd be very happy to find out about ways that I could improve or optimize it. I have actually previously done a whole series of tutorials about rendering water with OpenGL, which I'll link to in the description. And many of the concepts that I covered in those tutorials are relevant to this tutorial as well. So in this tutorial I'm not going to be going into those concepts in too much detail because I've covered them before, and also it took a whole 8-part series last time. So when I implement one of those concepts, I'll just give you a quick summary of it and then link you to the relevant tutorial in case you want to learn about it in more detail. And if you've never done any work with water in OpenGL before, then you might want to consider giving those tutorials a watch first anyway. Because there's just so much code to cover this week, I thought the best way of doing this tutorial would be to show you the process I went through to implement the low poly water step by step. Quite big steps because there's a lot to cover, but for each step of the process I'll give you an overview of the changes that I made to the code and explain why I made certain choices. In the description you can actually find the full code for each of these steps, which might have been a bit of an overkill, but I thought that some people might find it useful. And of course the fully commented final code is there as well. So if you just want to have a look through that, you can do that as well. So this is the code that I started with before implementing the water, and it's pretty much exactly the same as the code from the previous tutorial about low poly terrain. I've just stripped it down a bit to make it as simple as possible so that we can really just concentrate on the water this week. The first thing that I did to implement the water was to generate and render a simple flat mesh like this, which is basically like a flat terrain mesh. The mesh was generated in the same way that we generated the split terrain in the last tutorial, so each triangle of the mesh is a separate triangle and no vertices are shared between triangles. As we discussed in the last tutorial, this allows us to create the flat shaded effect. In the VAO, each vertex of the mesh has an X and a Z position and 4 indicator values, which I'll talk about later, but for now they're not actually doing anything. There's no need to store a Y position here because it's the same for all the vertices in the grid, so the water height is just loaded up as a uniform variable to the shaders instead. The code for generating the mesh is in the water generator class, which as I said is very similar to how we generated the split terrain last week, and it basically loops through each grid square of the mesh, gets the 4 corner positions, and then stores the vertex data for the 2 triangles individually. The XZ position of each vertex is stored in the VAO, along with those 4 indicator values which we'll need later, but for now I've just set them all to 0. There's also some really simple rendering codes which I don't think needs any explanation, with a very simple vertex and fragment shader, and again just note that these indicator values are currently not being used for anything, and at the moment they're all just set to 0. So after generating and rendering that simple mesh, I moved on to step 2, which was to set up a couple of FBOs and create the reflection and refraction textures. This is something that I covered in much more detail in the second water tutorial, but just to quickly recap, we basically take a picture of the scene, one from the camera's position and once with the camera's pitch inverted for the reflection, and that gives us 2 textures of the scene which we can then apply to the water's surface. We also render the depth buffer to a texture as well, so that we can use it for creating some depth effects. So in the render engine you can see that I set up a couple of FBOs with texture attachment color buffers, and one with a texture attachment depth buffer. You can make the dimensions of these FBOs smaller if you want to improve performance, but obviously that comes with a decrease in quality. During the rendering, the scene is rendered once to the reflection FBO and once to the refraction FBO before being rendered normally to the scene. And of course, during these 2 extra render passes, try to render as little as possible, as simply as possible to improve performance. So for example, during the reflection pass, you could just render the largest, most visible objects, and you could render them using simpler shaders, as the loss of quality won't be so obvious in the distorted reflection. So if I go ahead and run this, you won't be able to see any difference yet because those newly created textures aren't being used for anything, But if I comment out the main render pass and instead just blit the contents of the reflection buffer to the screen and then update the display, that will show us the contents of the reflection texture, which as expected is an image of the scene taken from under the water because the camera's pitch and its height was inverted before rendering. The next thing that I did was to apply the reflection and refraction textures to the water's surface using projective texturing, which is something that I covered in the 4th OpenGL water tutorial. To implement this, I first needed to get the textures to the Fragment shader, which I did in the usual way by linking the uniform samplers with a certain texture unit in the shader class, and then by binding the textures to the relevant units before rendering. Also, in the shaders, I passed the clip space coordinates of the vertex to the Fragment shader, where they get converted to normalized device coordinates by doing perspective division, and then we convert them to texture coordinates by using that conversion that we've used so many times before to convert from this coordinate system to this coordinate system. These can then be used as the texture coordinates for sampling the refraction and reflection textures, although for the reflection texture the y coordinate is flipped to make the reflection appear upside down. And there is a reason why I called it clip space real and text chords real, and that will become apparent later. But for now, you can see that I used those texture coordinates to sample the textures. I then mixed the results together and set that as the output. And as you can see, that has worked, so we can see both the reflection and the refraction on the water. But there is a bit of a problem, which is that parts of the terrain that are under the water are still getting reflected, and some parts of the terrain that are above the water are getting refracted. And that brings us on to step 4, implementing the clipping planes. If you want to learn more about clipping planes, then check out my OpenGL water tutorial number 3, but basically they allow us to specify a plane in the 3D world, and everything outside of that plane just doesn't get rendered. So I implemented clipping planes into the terrain rendering code, so now when rendering the reflection pass, we can make sure that only parts of the terrain that are above the water get rendered, and during the refraction pass, we can ensure that only things under the water get rendered. During the main render pass, we of course want everything to be rendered, so we just put all zeros for the plane, and for good measure I also enabled and disabled the clipping plane before and after using it. If I go ahead and run that, you can see that it's looking a lot nicer now, but there is now a new problem around the edge of the water, and this can be improved by adding a slight offset to the height of the clipping plane when rendering the refraction pass to make it slightly more lenient. You can also add a very slight offset to the reflection clip plane as well if you want, but be careful not to make it too big, otherwise you'll start seeing things reflected that shouldn't be reflected. The next step was to implement the Fresnel effect, which changes how reflective the water is depending on the angle that you look at it, and I talk about this in more detail in the 6th OpenGL water tutorial. This creates quite a nice effect already, but it will really start to make a big difference once the water is actually moving, as you'll see in a bit. The Fresnel calculation was added here in the Fragment shader, and as you can see it requires the vector pointing to the camera and also the normal vector of the water's surface. So these two values are now passed in from the Vertex shader. The normal for now I've just set as pointing directly upwards, and the to camera vector is calculated here by subtracting the vertex's position from the camera's position. And of course, the camera's position is now loaded up as a uniform variable before rendering. The result of the Fresnel calculation is then applied here in the Fragment shader, and it determines exactly how the reflection and refraction texture colors are mixed together. And if I go ahead and run that now, you can see that it gives us this nice effect. If you want, you can also change the bias of the Fresnel effect to make the water more or less reflective, so just play around with this constant here until you get something that you're happy with. So let's move on to step 6, which was to use the depth texture to apply some depth effects to the water, such as making the edges of the water a bit softer. This is of course completely optional. If you don't want to have soft edges, then you don't have to do this. I just think it looks a little bit nicer, especially when the water is moving. But totally up to you, make the edges as soft or as hard as you want. If you want to learn more about the depth effects in detail, then check out tutorial 8 of the water series, but I'll just quickly give you a summary now. So the water depth is calculated in the Fragment shader by this function here, which as you can see takes in those texture coordinates that we calculated earlier, and it uses them to sample the depth texture, which will give us the distance of the terrain from the camera. However, depth values in the depth buffer aren't stored linearly, So we have to convert it to a linear value using this code here, and this needs to know the distances of the near and far planes that we used for the projection matrix, so I pass those values in as a uniform. Once the actual distance of the terrain from the camera was calculated, I then calculated the distance of the water from the camera and subtracted one from the other, leaving us with this depth here, which is how much water is between the camera and the terrain. I then used the water depth value to set the alpha value of the fragment, meaning that lower water depths will have a lower alpha value, making shallow water more transparent. In the renderer class, I also had to enable alpha blending before rendering, and if I now run that, you can see the effect that it has, making the edges of the water much softer. And you can change exactly how soft they are by altering the edge softness value in the fragment shader. I also implemented another depth effect, which was to make the deeper parts of the water appear a little bit less clear and slightly murky. You can see the calculation for that here in the fragment shader, which simply uses the water depth to mix the refraction colour with the water's base colour, depending on depth. So down here you can see that I applied that effect, and if I now just use the refraction colour as the output, you can see that when I run this, it has made the deeper areas of the water look slightly bluer. I also then applied some general blueness to the reflection colour, and if I now display the final colour again and go ahead and run that, you can see that the water is starting to look very nice. So up till now I've just been implementing things that I covered before in my water tutorials, but I'm now going to show you the new things that I implemented to animate the water and to give it the low poly look. The first step that I took towards achieving this was to add some distortion to the water mesh so that it would now no longer be completely flat. This distortion is added in the Vertex shader, where I added this function that calculates an offset using a sine and cos function, using the x and z positions of the vertex as an input. This offset is then added to the x, y and z components of the vertex, and you can see that distortion being added to the vertex here. So now when I run this, you can see that the mesh has been distorted into this sine wave-like shape. However, the water still isn't moving, so I then implemented a value that changes over time into the distortion calculation. This Wavetime uniform is simply increased every frame in the water renderer class, and then loaded up to the shader as a uniform. This means that the input of the sine and cos functions are now changing every frame, meaning that the distortion for a given vertex is now also changing every frame, which gives us this effect. As you can see, the water is now wobbling around very happily, but there is still one slight problem, which is that the reflection and refraction aren't being affected by this movement, as if the water were completely still. This is because we use projective texturing, so the reflection and refraction textures aren't really attached to the water mesh in any way. They're basically just being projected onto it from the camera's viewpoint. So it doesn't matter what the shape of the mesh is, it's like a film being projected onto a bumpy wall. The texture is always going to appear perfectly to the camera, which is really the whole point of projective texturing. So to fix this issue, in the Vertex shader I calculated the clip space coordinates for the vertex again, but this time I calculated them before applying the distortion to the vertex, so these are the clip space coordinates of the vertex as if the vertex were still in the flat grid. These then get passed to the fragment shader as well as the actual clip space coordinates that we were using before, and I then use these new clip space coordinates to calculate a second set of texture coordinates, but this time the projective texturing hasn't taken the distortion into account. I then used these new texture coordinates to sample the refraction and reflection textures, and this time when I run this, you can see that the textures do move with the waves. So because the distortion now has no effect on the calculation of the texture coordinates, the textures are basically stuck to the vertices because the texture coordinates aren't changing. So when the vertices move, the textures now move with them. Of course, this doesn't actually create physically accurate reflections, but it's still a lot better than having totally still reflections, and it's just a nice, quick and cheap way of doing it. Also, just note that I'm still using the other texture coordinates to sample the depth texture, because we do want to take the distortion into account when calculating the depth, and your soft edges won't work as well if you don't. Finally, there is now a slight wobbling effect around the edge of the screen here that we want to get rid of, and that can be fixed fairly easily by clamping the texture coordinates a bit. So we're almost there now, but there is still one thing missing, and that is lighting. And in order to apply lighting to the water, we need to know the normal vectors, and these normal vectors will of course have to be calculated after the distortion has been applied to the vertices. One way of doing this would be to use the geometry shader, and if you would like to go down that route, then you can check out my geometry shader tutorial, because I gave an example of exactly that in that tutorial. However, as we saw in the previous tutorial, using the geometry shader can be rather expensive, and it would be better if we could somehow calculate the normal vector in the Vertex shader. In order to calculate the normal of a triangle, you need to know the positions of all three vertices, but unfortunately in the Vertex shader we only have access to one vertex, the current vertex being processed. We don't have access to the other vertices of the triangle, so we don't know where they are. And that is where these indicators come into play. For each vertex in the mesh, we're going to store 4 extra values which indicate where the 2 other vertices in the triangle are. To do this, we're just going to provide the x and z offset of the 2 other vertices in relation to the current vertex. Or in other words, the indicator contains the 2 vectors going from the current vertex to the 2 other vertices, and I think this diagram here explains it better than I can. So for example, if we want to get the indicator for this vertex here, we need to find the vector from this vertex to vertex 1, which is this, and the vector from this vertex to vertex 2, which is this, and then we simply store those 2 vectors in the indicator. And if you're familiar with basic vector maths, you'll know that we can find the vector going from one point to another by simply subtracting one point from the other. So in the water generator class, you can see that I did that here to get the 2 offsets, and then the 4 values just get stored all together in the VAO. Also, because we don't want to be wasteful with memory, we can store these values in the VAO as 4 bytes instead of 4 floats. So that's what I'm doing here, and then when you store the data in the VAO, you're going to need to indicate that it's byte data instead of float data. This means that the entire vec4 of indicators is just a total of 4 bytes, which is the same as having just 1 extra float attribute. If we wanted, we could probably squeeze all the data into a single byte by encoding it and then decoding it in the shader, but from what I understand, this wouldn't actually save any memory because OpenGL requires the byte size of attributes to be a multiple of 4. So if you had an attribute that was just 1 byte, OpenGL would add 3 bytes of padding so that it would be 4 bytes in total anyway. I'm not totally sure if this is the case because I couldn't find much information about it, but I'll put a link in the description to the article that seems to be suggesting this. Anyway, now that we've got the offset data in the Vertex shader, we can add each offset to the current vertex to get the original grid position of the other 2 vertices in the triangle. We then need to apply the distortion to them as well to find out what their position is in the distorted mesh, and now we can finally calculate the correct normal. This then gets passed to the Fragment shader, and for now I'll just put it as the output, so that you can see that the normals are indeed being calculated, which is great. And if I change this back to outputting the final color, you'll see that we can finally actually see the waves of the water. And at this stage it's interesting to note that there's still no lighting on the water at all. The only reason that we can see the waves now is because of the Fresnel effect, which is now using the correct normal vector. If I instead remove the Fresnel effect and run this again, you can see just how much of a difference the Fresnel effect was actually making. Now that the normal vector was calculated, I was able to calculate some per vertex lighting for the water, and you can see in the Vertex shader here some calculations for both diffuse and specular lighting, and up the top here there are a few more constants that you can play around with to change the shininess of the water. I also had to load up a couple more uniform variables with information about the light in the scene. The results of the diffuse and specular calculations get passed to the Fragment shader, and the lighting is then applied to the final color here. And now if I go ahead and run this, you can see that it's a bit of an improvement. You can see some diffuse lighting in the waves here, and at certain angles you'll be able to see the specular lighting, but it will look even better in a minute. So the final thing that I did to get the low poly water effect was to mess around with the distortion code for ages until I came up with an effect that looks pretty random. And it's not perfect, you can still see occasional patterns in the water, but in general, from most camera angles, it looks pretty good. But you can play around with that distortion code and see if you can get it looking a bit more random and more optimized if possible. I think you could probably also achieve a similar effect in a cheaper way by making use of noise in the shaders, but that's not something that I've ever tried myself. But if you do get it working with noise, then please do let me know, because I'd love to see how you did it. One thing that you could do if you wanted to make this a little bit less expensive would be to only apply an offset to the Vertex's Y component and not to the X and Z components, which still looks pretty good, but it's just a little bit more rigid. Another thing that you could consider doing is making these 2 extra render passes a bit more optimized, and I'm not sure if there's a way to do them both in one go by rendering to multiple color buffers. Maybe it works, I'm not sure about the clipping planes though, or maybe somehow you could do the refraction pass and the main pass at the same time, but it's not something that I've ever managed to do before myself. You could also try and use a screen space reflection method, which would definitely be cheaper, but again, it's not something that I have experience with. But I believe that you would have some problems with reflections of things that aren't on the screen. So for example, this hill here, I think its reflection would just disappear when it goes off the screen, but I'm really not sure. This is just one thing that I read from one article, and there may well be ways of getting around that. Finally, you could also just leave out the refraction pass altogether and just use alpha blending to make the water appear transparent, using the Fresnel effect to determine exactly how transparent it should be. Obviously, the refraction wouldn't be distorted then, but it would definitely improve performance. So I think that is pretty much it for this week. As I said earlier, this was just my implementation of this, and I'm sure there are many things that could be improved or optimized. So if you know of any, please do let me know, because I'd love to be able to improve on this. Also, I'm sorry that the tutorials have been taking so long to come out recently, but not only do they take ages to make, but I'm also pretty busy at the moment trying to finish and prepare for the release of my game Equilinox. But I am still working on the tutorials, and I will try my best to get a couple more done before the end of this year. For this video though, that is it. Thank you guys very much for watching this video. Do subscribe if you haven't already. Have a wonderful week, and I will see you all next time.